Hello and welcome to the Further Maths Support Programme revision recordings. In this session we're going to be looking at MEI Mechanics 2 and in particular we're going to be looking at the work, energy and power topic. These are the basic concepts that you need for work and energy. You need to be able to calculate work done by a force moving along its line of action and at an angle to its line of action. You need to be able to calculate kinetic energy and to understand mechanical energy. You need to be able to understand the work energy principle and to have an idea of conservative and dissipative forces. You need to be able to calculate gravitational potential energy and to be able to solve problems which use the principle of conservation of energy. And you also need to understand the concept of power, that it's the rate at which work is being done, and you need to be able to apply that in a range of different problems. So we're starting off here with a question from a past paper. This is just an excerpt from this particular question just to give us an idea of some first moves in here. If you're going to be working on this at home, please do pause the recording at this point and have a go at the question yourself. I'm going to be starting the solution right away. So the parachutist and her equipment are falling through this height of 1,600 meters. Her speed is reducing and work is being done against resistances. So thinking about the energy method that we're going to use here, I like to think of this as input energy equal to output energy. Now that doesn't necessarily mean that energy is being conserved because there is work being done by external forces in this system. But input energy is any energy that the system has right at the beginning, and added to that any energy which is any work which is done to increase the total energy of the system. So in this particular case we've got an initial kinetic energy and we've got initial gravitational potential energy, but there's no engine adding any energy into the system, so there's nothing further to add in the left hand side of this equation. On the right hand side though, we do finish up with final kinetic energy. We've lost our gravitational potential energy, but work has been done against resistances, so work done versus resistances. That goes into the output energy. It's energy which is removed from the system by that external force. Okay, so let's substitute some values in here. Initial kinetic energy given by half mv squared, so in this case half times 80 times that initial speed v squared. Gravitational potential energy is going to be 80 times 9.8, this is mgh, the height it's dropped through 1,600. Final kinetic energy is going to be half times 80 times that final velocity, which is 6 squared. And work done against resistances, well, we're told that we don't even need to do force times distance moved in this case because we're given a specific value of the work that's been done. Rearranging that expression then and simplifying, popping it into a calculator gives us v squared is 1,176, and that gives us v is 34.3 meters per second. So that's just a little warm-up looking at some concepts of energy, and we're going to go on and do a little bit more work on power. Okay, so a long question this time. We have a car of mass 1,200 kilograms, travelling on the road for 2 minutes, and it's rising through a distance of 60 meters and doing work against resistance to motion. There are a range of questions here. If you want to pause at this moment and read through those in detail, please do so. I'm going to be going through each of these sections of this question one by one. Okay, so the car's travelling along the road for 2 minutes, during which time it rises vertical distance, etc. We have to calculate the average power developed over the 2 minutes. Now, power is rate of work being done, so average power can be worked out by calculating the total work done and dividing that by the total time. So let's just make a little note of that. Power is going to be total work done over time, and the work done in this particular case comes in two forms. It comes in the form of gravitational potential energy, which has been gained, and work done against the resistances. So let's put some values in there. Gravitational potential energy gain, so mgh, that's going to be 1200, that's the mass, times 9.8, multiplied by the height it's risen through, which we're told is a vertical distance of 60 metres. And we're going to add that work done against resistances. Well, again, they're giving us the value of that work done against resistances, 1.8 times 10 to the 6. And we're going to divide that by time. Power is measured in watts, which is a measure of joules per second, so we need our time to be in seconds. That's 120 seconds. And if we pop that into a calculator, we get 20,880 watts. And if we like, we can write that in kilowatts. So 20.88 kilowatts, or 20.9 kilowatts if you want to go to three significant figures. A little word on the mark scheme for that one. We've got 4 marks for this. We have a mark for calculating the gravitational potential energy. We've got a mark for the overall, a method mark for the overall idea of work done over time, and we have a B1 mark for the 120 seconds, knowing to turn it into seconds instead of minutes, and a final answer mark here for our last answer. Okay, going on from there. So we're now having the car travel along a straight level road at a speed of 18 metres per second, and notice that that's a steady speed. It's developing this constant power of 13.5 kilowatts forward. That means that there is some kind of tractive force acting here in the system, and we have a resistance to motion, which I'm going to call R, when it's travelling at 18 metres per second. Now notice that it says it's travelling at a steady speed. That means that T, our forward force, our tractive force produced by the engine, is going to have to be R. It's going to be equal to those resistances because it's travelling at constant speed. There's no acceleration, so there can be no resultant force forwards. So that's a nice little start there. We can also get a relationship between the power and the tractive force and the velocity. We know that power is tractive force times velocity, so substitute into there. Remember again, standard units are watts for power, so 13,500 equal to our tractive force times 18 metres per second. That gives us T equal to 13,500 over 18, which means, and that's equal to 750 newtons, so we know that the resistances are also equal to 750 newtons. Okay, how much work is done against the resistance when the car travels 200 metres? Well, if we have a constant resistance to motion, work done equals force times distance moved. So in this case, that's going to be 750 newtons multiplying 200 metres, which gives us 150 kilojoules, 150,000 joules, or 150 kilojoules there. Little allocation of marks note there. Using the power to get our tractive force gives you an M mark. Knowing that R is equal to T at constant speed gives you an E mark. And calculating that value of the resistances gives you an A mark. Knowing that work done is force times distance moved is an M1, and you get a final F1 mark. That's following on from your answer to the first bit of the question for giving the correct answer at the end there. Okay, so now the car travels down a slope inclined at 5 degrees to the horizontal. I find it very hard to draw a 5-degree slope, so I'm just going to put it in as shallow as I can make it without it becoming overcomplicated. So here's my car travelling down the slope this time. It starts at 18 metres per second, and we have the brakes being applied, and the brakes are producing a total resistance to motion of 1500 newtons, but no other forces. I'm sorry, that's not true. There will also be a weight, obviously, acting in the diagram. So we want to know how far it travels down the slope before its speed is halved. We're going to do this again by energy ideas, so input energy equal to output energy. And I'm going to say that the car travels a distance d down the slope. So this is going to be particularly useful for working out some of the values that we're looking for in here. So it's going to travel a distance d down the slope. It starts off with, initially, with kinetic energy because it has speed, and gravitational potential energy, because it's sliding down the slope. We've also on the other side then got final kinetic energy because it is still moving, but our gravitational energy has all been converted. We also lose energy to resistances, so we've got work done against our resistances going on as well. So let's substitute some values into there. Kinetic energy is going to be half mv squared. Our mass in this case is 1,200, and our initial speed there 18 meters per second squared. Our gravitational potential energy, mgh, well, this is going to be m, that's our 1200, times 9.8. Now the height is going to be d sine 5. If you imagine you've got your triangle here, the hypotenuse of the triangle is d, so the opposite, the height that we're looking for, is going to be d sine 5 degrees. We don't know our value of d, that's what we're looking for, so just going to have to leave it as a variable for the time being, an unknown rather for the time being. Final kinetic energy, half m times 9 squared. We wanted it to halve its speed, so we're taking it down to 9 squared. And the work done against resistances, again, work done force times distance moved. You know that the force that it's using to overcome those resistances is 1,500. Distance moved is d. So our unknown value d appears on both sides of the equation, so we need to do a little rearranging here. So d, and I'm going to factorise as well. I'm going to take everything to do with d onto the left-hand side, everything to do with d onto the right-hand side, and everything else onto the left, as it is in this line. So that's going to give me d times 1,500 minus 1,200 times 9.8 times sine 5. And on the other side we're going to have half times 1,200 times 18 squared minus 9 squared. That's just dealing with the kinetic energies there. And if we pop that into a calculator, that's going to give us our distance d, 306.91, So our distance, we'll go to three significant figures, 307 meters to three significant figures. Allocating some marks there. Method mark for using the energy calculation. A mark for correct kinetic energy terms, a method mark for coming up with a gravitational potential energy expression that involves a resolution, and an answer mark for having that correct, an A1 mark, an answer mark for having the whole of the calculation correct, and then a final answer mark for the 307 meters, dependent on rounding. The car's travelling now along a straight level road. We're almost there. This is the last little section of this question, and it's developing a power P, so we're generalising a little bit more in this part of the question, and it's travelling at v meters per second with acceleration a meters per second squared against a resistance of r newtons. So again, we know that we've got a forward tractive force acting here, and we can find an expression for that tractive force which connects P with the velocity. We know that P equals TV in this case, so our tractive force is going to be P over V. We can then use a little Newton's second law because we know it's accelerating. So Newton's second law, forward force is going to be P over V, resisting force is R, and that's going to be equal to mass times acceleration. So mass 1,200, acceleration A, Little rearrangement on that. If I multiply both sides by v, I end up with p minus rv equals 1200 AV, and that can be rearranged nice and easily to give the expression that we've got up in the question. Times by v. Okay. Last little bit there, deduce that if p and r are constant, then if a is non-zero, it can't be constant. Okay, so let's have a little think about that. If a is non-zero, that means that there's an acceleration of some kind. If there's an acceleration of some kind, then v varies. Okay, so v varies, the velocity varies if there's an acceleration. That means then that looking at this calculation that we've got here, this formula that we've got here, if p and r remained constant, but v varies, well, the only other thing that can vary in here is a, so a must vary because v has to vary because a is non-zero. Okay, so allocating a couple of marks there, you get a B1 mark for the expression for the for the tractive force. Another B1 mark for using Newton's second law in here, an E1 mark for showing the result that they'd asked for, and a nice E1 mark for explaining that if A is non-zero, V must vary, hence both V and A must vary. Okay, so that brings us to the end of this particular section. There are other videos available at the same site, and I do encourage you to take a look at our home site www.furthermaths.org.uk. There's lots of goodies in there for teachers and for students. I hope you found this useful, and thank you very much. Goodbye.